Logarithms. Let's look at graphs of logarithms. Now, logarithms are inverses of exponentials. So I have our graphs that we did earlier from our exponentials. Here's our log graph. Y equals 2 to the x power is the inverse of log base 2 of x. So these numbers, these x and y values for 2 to the x power are going to swap so that our y's become our x's and our x's become our y's. So that helps us know what we should plug in. In general, you take the base and the numbers you plug in have to do with the base. So for example, I just want to make this screen bigger so I can see better what's happening. So 2. So a number that's related to 2 is 1/2 or 0.5. And the power that would give us 1/2 is a -1 because it's a -1 power that would flip over 2 to turn it into a 1/2. So it's about what the power is going to be on the base to get the number that you put here. 1 is always a good number because anything to the 0 power is 1. Since our base is 2, 2 is a great number to use because that's to the first power. 4 is a good number to use because 2 to the second power is 4. So you see how we're going backwards and figuring out the exponents that give us these values. So the values we're plugging in are the numbers we would get from using exponents on a base of 2. Okay, let's graph these. So 1/2 and then -1 and then 1, 0 and 2, 1 and 4, 2. So there's where our graph looks. Oh, that didn't go very well. Let me redo that if I can. There, that's a little better now. The problem with this graph is that it's actually going into the y-axis, and it shouldn't be doing that because there's going to be an asymptote there. Okay, let's look at the next one. For a base 5, let's do 1/5. Let's do 1. Let's do 5. That's probably enough. So to get 1/5, 5 to the -1 power is 1/5. 5 to the 0 power is 1. 5 to the first power is 5. Let's plot those numbers. 1, 0, 5, 1. And so our graph, notice it's very similar to the one we just did. It's just flatter. So like I said when I had to start this unit, it has to do with stuff that's happening in the world because we're trying to go from cases of coronavirus growing exponentially, which is what they're currently doing in the US, and kind of unstoppably increasing every day, to what they keep saying, flatten the curve. We want our exponential function to be more of a logarithmic function where, yes, it grew a bunch and now we want it to flatten out so that there's no more new cases or that they become fewer and fewer all the time. Okay, let's look at what happens if our base is a fraction because that's going to be the inverses of the other two problems we looked at. So I think, see if I can find them. They're in here somewhere. So those, yeah. So see, these were decay. So these logarithms are the inverses of exponential growth. So what's the inverse of exponential decay? So let's look at these. I'm going to do a 4 and a 2 and a 1 and a 1/2. So if I plug in a 4, 1/2 to what power is 4? Well, it would have to be a -2 because we would need the negative to flip it over and 2 squared to get the 4. And then to get 2, we're just flipping that over, so that's a -1. And to get 1, that's a 0 power. It's always a 0 power. And then to get 1/2, that's just the first power, because 1/2 to the first power is 1/2. Okay, let's graph these. So 4, -2, 2, -1, 1, 0, 1/2, 1. So you can see it's just like our logarithmic graph, but it's flipped over the x-axis. Let's do our 1/4. So I'm just going to start with 4. That would be a -1. And then 1 is 0. And 1/4 would be 1. So that gives us this graph here. 4, -1, that's in the wrong place. and 1, 0, and 1/4 1. So yeah, again, we've got that upside down logistic graph. So you can see how this one's flatter than this one because 4 is bigger than 2. This one's steeper, this one's flatter. The 5 is flatter than the 2 is base 2. Earthquakes are measured in a logarithmic scale base 10. So because of that, every time you go up a number on the seismic scale, like from a 4 to a 5, that's actually 10 times the energy in the earthquake. All right, let's look at properties of logarithmic functions really fast. So we've got our domain, which is from 0 to infinity instead of negative infinity to infinity. The range is now from negative infinity to infinity. Remember, because these are inverses, they're just trading the domain and range. Everything's trading from the exponentials. There is now an x-intercept, and it's going to typically be at 1, 0, because anything to the 0 power is 1. And we'll have an asymptote at the y-axis, so there's no y-intercept. So we get a vertical asymptote, and the vertical asymptote is going to be at x equals 0. So let's look at how these are going to work. If b is greater than 1, we have our point at 1, 0. And then we're going to have another point. Ignore the grid for me. I'm just going to put a point somewhere. And we're just going to say that this point is at b, comma 1. So whatever your base is, you go over the base and up 1, and that gives you another point for your graph. Then we have our asymptote at the x-axis here. So our graph will follow approximately like this. Okay, so that's if b is greater than 1. That's typically what we're dealing with. We don't usually deal with bases that are fractions, but just in case we have a reflection, let's go ahead and throw our asymptote in there again. And we've got our intercept at 1, 0 again. But this time, because of the fraction, it's going to be flip the fraction over to get the number and then go down 1. Or you could kind of just go backwards because it would be over that fraction amount up 1. So it would be like in there. But I prefer to kind of just say, you know, that point over here is going to be 1 over b. It's the reciprocal of it, comma negative 1, causing our graph to look more like this, reflected over the x-axis.